And welcome everybody to our final class of data structures. I'll just go ahead and start sharing my screen. This last class, what we're going to talk about, do a quick wrap up of the things that we've talked about all semester. What are the key highlights to take away from this course? And then we'll talk about a little bit more about the final exam, have a chance to work some sample problems, and that'll be it for the semester. Yeah, I've really enjoyed data structures. It's one of my favorite classes to teach because we get to talk about a lot of really cool things. I really like the, well, I guess I like all the classes that I teach, but the data structures class in particular, it's sort of like the transition from, you know a little bit of programming before this class, but I mean, realistically, not all that much. If I was working on a say a research problem and working with you all before data structures, I wouldn't have had too much faith in your ability to complete the problem realistically. But now that you've taken data structures, you've done a lot of hard things. You've made it through the AVL tree and the heap and the binary search tree, and hopefully not with too many scratches. So now I have a lot of confidence in all of your programming abilities. So you should all be feeling pretty good about yourselves for having completed those assignments. Let's see, let's scroll down here to some of the big ideas. So one of the key, I guess, concepts from this class is that every data structure, it has these operations on it, like whether you're inserting into a list or indexing from it or whatever the operations are, and they all have their different runtimes, and you really need to know what those runtimes are. And that's one of the things that's going to really separate the sort of advanced Python programmer from the beginner Python programmer, is that because you know what the runtimes of these data structures are, you know when is it appropriate to use a list versus a deck or this NumPy array, which we talked very briefly about at the beginning of the semester. In these three cases, list and deck and the NumPy array, they have the same interface, so you can always use one instead of the other, but depending on which one you use and depending on exactly what your code's doing, one of those will be potentially much, much faster than the other. And in the world of data structures, we like to say that there is no free lunch. No matter what task you're doing, there's no like one data structure that is the perfect data structure for everything. It's always going to depend on your particular application and its needs. And so you really need this toolkit of a handful of data structures that you can draw on. And throughout this course, we've talked about a lot of them, the list, the deck. Those are the two big, what we'd call the linear data structures for storing just information inside of a linear sort of thing. And the main idea, the main difference in these is that the list you have random access to, so you can get things from the middle of a list really efficiently. And so a list is also good for binary search, because in a binary search, you need that random access. You need to be able to access anywhere in constant time. The deck doesn't do that. The deck has bad performance when you're accessing in the middle of it. But the advantage of a deck is that you can add on both ends of it, append and remove to both ends really efficiently. So the deck is often the implementation for a queue. Whenever you see a queue, you should probably be thinking deck. One of the easy ways to remember that is that it has a part of the word queue inside of it. So that's kind of my mnemonic that helps me remember that. And this word list, or this data structure list, this is another sort of Python specific thing to just remember that if you ever go to a different programming language and it has lists built into it, it might not have the same runtime characteristics as the Python list. And in particular, if so the C and the C++ programming languages and Java, three very popular programming languages, list means something different in those languages, and what they call an array is what in Python we call a list. So anytime you're learning a new programming language, if you do learn one in the future, that's another one of the key things to just be aware of and keep in mind as you're learning. What are the runtimes of each of the default data structures in the language? One of the things that we haven't really talked too much about is sort of quadratic runtimes and how they are the worst. And what's bad about them is that they're fast enough that you don't really notice a problem at first when your in value is small, like 100 or 10. It still runs really fast. It almost doesn't really matter what your runtime is going to be on those things. But once you get a lot of data, things get really, really slow. And this is something that happens all the time in practice, that people create an algorithm or write some code. They think it's fast, but they haven't done a proper asymptotic complexity analysis of it, just blindly writing code. And it turns out that their algorithm is quadratic when it should have been linear. So as an example, on Microsoft Windows, so this was a problem actually in the most recent version of Microsoft Windows. This bug was just discovered a couple of months ago. And it turns out if you had a lot of icons on your desktop, then your computer would just slow down to a crawl. And this bug right here was actually first discovered or announced with this tweet right here. So end of January 2021. And so this person has a super expensive computer and it's taking a long time to do things. And there's this other blog right here by this guy of the name Bruce Dawson. And he has a number of these posts analyzing performance problems inside of Windows. And he saw this tweet and did some analysis and was able to show that the problem was that Microsoft Windows was using a quadratic algorithm to decide where to place the tiles on the desktop. Most people have less than 100 tiles on their desktop, less than 100 icons. And so this had never come up before, but this other person had somehow put 10,000 things on their desktop. And so it was triggering this worst case quadratic performance. If you've ever played the video game GTA Grand Theft Auto, they also recently had a accidentally quadratic bug discovered. And here, so load times, loading up a new level in GTA was taking up to 7 minutes on people's computers. And some random, somebody who I would call a random hacker, was trying to figure out why was this the case. And so they were looking through the executable file for GTA and discovered that they were doing something in quadratic time that they could have been doing in linear time. And so he fixed this for them, not a GTA employee or not an employee of the company who writes GTA, but reduced that 7 minutes load time down to instantaneous just because of changing that code from quadratic down to linear. Stack Overflow, so the website that you've probably referenced several times throughout this course, also recently had an outage. They crashed for about 15 minutes because in their web page for the code that renders the web page, they were doing something quadratic, and somebody created a post that triggered that quadratic behavior, causing the system to crash. One of the sort of best ways to kind of level up as a programmer at this point for you all is to read some of these case studies about things that other people have discovered as problems in their code, and see how they not only fix the problem, but how did they even discover that it was a problem in the first place? And what was their thought process like as they went through and did these debugging experiences? If you do choose to visit any of these links and read them, the sort of techniques that the people are using to do this debugging are relatively advanced techniques, so you don't expect to fully understand everything inside of it. But you should be able to understand now the principles of why was this certain section of code slow, and how did they figure that out using the asymptotic analysis. And there's this really famous blog that basically every programmer in the world knows about called Accidentally Quadratic, where people have lots and lots of stories like this about things that should have taken linear time, should have been fast, but somehow quadratic code got got pushed into production and brought production servers down. So there's a fun one to read whenever you're done with finals and done with the semester, but still wanting to do more data structures and level up as a programmer. Let's see. So I said that there is sort of no free lunch. There's no one thing that is perfectly good in all situations. But the thing that comes closest to that is binary search, and in particular the AVL tree. If there's one thing to take away from this course, it is just that that is a magical algorithm. Taking the runtime of linear runtime, having to scan through, like say your Google, instead of scanning through everything on the internet, being able to do that and log in time with this binary search algorithm and tree is, I don't know, to me that just seems magical, because login is just so fast. It doesn't matter how big the internet grows, how many billions upon billions of web pages that is. When you take the log of that number, you still only get like 10 operations that you need to do to search it all. And that still blows my mind. And yeah, so this sort of divide and conquer binary search AVL tree is the foundation for a lot of really cool things in computer science, and every company has this going on inside of their code base somewhere. When you go on software engineering interviews, whether it's for internships or like future jobs, one of the reasons that these binary search divide and conquer data structures questions are so common is because it is so foundational to everything that those companies do. Let's see, another big picture concept, and this is especially for people who are going to be going on to taking future courses in computer science, especially like the data mining course, is that these big O and omega and theta notation. Again, if you read just sort of random blog posts on the internet, especially like lower level blog posts, you're going to see a lot of kind of misinformation about these concepts. These concepts do not originate with computer science. They do not originate with analysis of algorithms. They have a history going back in mathematics far longer than that, and mathematicians still use them for all sorts of different applications. And computer scientists still use them for all sorts of different applications. And if you do take the data mining class, we'll be using this sort of notation for analyzing convergence speeds of statistical properties of algorithms, lots and lots of things other than just what is the runtime. And so it's really important to understand that what the mathematical definitions of these concepts are and sort of their broad applicability. We'll talk about the final exam here in a little bit in more detail. And again, this is really the key concept for the final exam, that if you understand the big O, omega, theta notation, then you're going to get an A on the final. And if you don't, then you're not going to do well on the final. Let's see. So compared to other computer science data structures courses, so like the ones taught at MUD and Pomona, we've actually covered quite a lot more material, even in this kind of online, slightly abbreviated format than other data structures classes, and in particular focusing on real-world tools that you'll use. Well, you can use them for anything for your own personal projects, but if you do go on to a software engineering or data science job at a company, then you'll be using these tools every day professionally. So things like Git for managing your own projects and collaborating with other people. This idea of test-driven development and continuous integration. So continuous integration, the tool that we were using for that is GitHub Actions. But this idea of just having test cases, and you know that you're done programming when you've completed those test cases. That is like, it's very tempting for, I think, more junior people to start programming a problem without having test cases. You feel like you're making more progress on the problem, actually accomplishing something tangible. But you don't know like that you're actually making progress when you do that, because you don't have any proof. You can't run tests to have evidence that your program was successfully doing things now that it wasn't doing before. So one of the sort of like hallmarks, or one of the things that really separates junior developers from more like middle career developers, is this habit of writing good test cases all the time. Any project that I'm working on personally, the very first thing I always do is create test cases for it. Actually, like, let's say one of the things we did not talk too much about in this course is how do you actually create test cases. That you used a lot of test cases, but I never asked you to create your own test cases. And there is a real art to doing that, and it's something that they just have to practice and get feedback from more senior people. But again, keep this as a tool in your back pocket, no matter what you're working on. We also talked about creating and publishing your own Python libraries. That's something that other data structures classes, and actually an entire computer science curriculum, very few CS curriculums talk about this like actual practical aspect of programming. How do you create your own packages and distribute them? But you all know how to do that now. You've done that. We talked a lot about open source and the different philosophies behind it, licenses that you can choose. When we did the Twitter assignment, we did Mapreduce. And this is one of those things that is really good, like for your resume and for interviews when you're talking about your experience in the interview setting, bringing up the fact that you've done Mapreduce projects, that the data set that you're analyzing was about 1 terabyte large, all tweets sent over the course of a year. Mapreduce really popular inside of industry companies. Actually, in my opinion, it's a little bit too popular these days. It's kind of definitely a little bit overhyped. And if you do go on to take the big data course, one of the things that we'll be talking about is like the alternatives to Mapreduce and how you can make this project that took a couple hours with Mapreduce, how you can make that happen in milliseconds by properly taking advantage of AVL trees and binary search. Yeah, so that's like, in some sense, the key idea of the big data class, if you go on to take that, is replace Mapreduce with binary search trees, and now things take milliseconds that used to take hours. We also talked a lot about, maybe not a lot, but a little bit, an introduction to bash scripting, specifically with the Mapreduce and Twitter assignment, getting you some good exposure to that. If, yeah, in terms of like programming languages that are really good to know, let's see, I don't know whether Python will exist 20 years from now, but I'm 100% confident that bash scripting will exist 20 years from now. It is, in some sense, the original programming language that glues together the entire operating system of Linux and any Unix system. And so it's gonna be staying around forever, and whatever time you spend investing in that is going to pay back big dividends for you in future projects that you do. And we also talked a lot, one of my favorite subjects, one of the subjects that's also just totally ignored in most computer science curriculums, is Unicode and non-English languages. There's another thing that we'll talk even more about in both the big data class and the data mining class, if you go on to take those. So how do you quickly search through, like Google does, lots and lots of documents written in lots and lots of different languages? Or how do you apply machine learning algorithms to things other than just English, but also to Spanish and Korean and your favorite language of choice? These are really important, again, from a practical perspective, that when you write your code in the future, whether it's data science code or more traditional software engineering code, because of the internet, your code is not just going to be like available for Americans, it's going to be available for anybody in the world. And just by being aware of the general techniques of Unicode and how to make that code accessible to other people, you can avoid making a lot of mistakes that will make your code inaccessible to those populations. Let's see, so some of the things that we didn't cover, again, this class really oriented towards the data science spectrum of things rather than the traditional software engineering spectrum. And what's normally covered in that more software engineering spectrum sort of classes is more details about memory management than we covered in this class. And in particular, because we use Python, this is what's called a garbage collected language. So Python actually manages most of the memory sort of issues for us. We saw at the beginning of the semester, it doesn't handle everything for us. We still have to worry about copying and deep copying and issues like that. But if we were in a language like C or C++, then there's just a lot more issues that go on with that. But that's not needed for data science at all, so we didn't talk about it. Another sort of big picture principle from this course is that you really want to master your tools that you're using, that good tools really make you a lot more efficient as a programmer. So the first recommendation, let's see, I have a lot of recommendations and I'm very opinionated on my tools. When you go on, say, software engineering interviews, one of the things that people want to see is that you are opinionated about your tools. In a sort of humble sense that you know what tools you like, but you don't want to like insult other people who are necessarily using different tools. But the fact that you know what tools you like and you've learned them is a good indicator that you kind of separates you out from other people who maybe have been less involved in selecting what tools they're actually using. If you've spent time using the tools and really learning to use those tools well, then that is an indication that that you just enjoy programming more and so are going to be more productive as an engineer. So one of the reasons why I like Linux, well, there's lots of them, but even Microsoft actually uses more Linux than Windows. And so if it's the case that Microsoft uses more Linux than Windows, then I can't think of a better endorsement for Linux because Microsoft makes their money on selling Windows. And so if you follow this link right here, it explains all details about that. Yeah, if you're looking for things to do over the summer to become a better developer, better data scientist, one of my definite recommendations is to install Linux on a computer and use that as your primary system. You'll learn a lot of sort of just very subtle things that will definitely help you out in either future courses, if you take them with me, or just future software development projects. So definitely recommend installing and using Linux. Other recommendations. So I hope I've convinced you a little bit of in this course that Vim is a more powerful editing tool than VS Code or whatever you might have used in the past. And I would personally recommend that you stick with using Vim. But whether you stick with Vim or choose a different tool, you should really invest time in actually learning the tool. Watch some YouTube videos of people using it, see what sort of tricks they use, and add those tricks into your own vocabulary of things that you use. If you're doing Vim, you should probably, now would be a good time to go back to that Vim tutor program, rerun it, and you'll see that like you actually have forgotten 90% of the things inside of Vim tutor. There's also, yeah, on YouTube, lots and lots of good streams of people just showing, here's a lot of cool tricks with Vim. And in class, I tried to show some cool tricks, but it's probably maybe like 5% of the tricks that I have in my back pocket of while I'm programming and using things. And I'm not even particularly advanced with Vim. So lots and lots of room for you all to improve here and get more productive. With version control and Git, there's another one of the things that's tempting for students and junior developers to kind of ignore, is that you think that the projects you're working on are small enough that you don't need Git version control, so you just don't do it. But my recommendation is any project you're working on, put it in a Git repo. And this is good for both like actual source code related projects and non-source code projects. So yeah, a lot of you have just recently completed your senior thesis. But for those of you who are going to be doing one in the coming years, a senior thesis is a great thing to put into a Git repo that you can version track your changes, easily collaborate with whoever your advisor is, put it up on GitHub, share it with the world. Lots and lots of advantages to version control. Another sort of thing that students often do is, okay, even if you're using Git for a repository, you feel like you should make it either not put it on GitHub or put it in a private repo in GitHub because it's not like perfect yet and you don't want to share it with the world. And my personal philosophy, at least, is that everything should be shared with the world unless it has secrets in there that specifically can't be shared, like passwords or something. And so I don't know, at this point in my career, it's probably like maybe once or twice a month that I have random people on the internet contacting me about my Git repos on GitHub and either saying that they really appreciated it or wanting to collaborate somehow on it. But even when I first started using Git maybe 10 years ago and putting things on online, I was surprised at like how often I got feedback that way. Is there a question? Okay. So where to go from here? I guess the three main next courses that build off of this course at CMC are the big data course and the data mining course, both of which again I teach. And again, sorry about data mining not being next fall. Still not sure whether it'll be a spring course or whether somebody else might come in the fall and do it. But big data will definitely be next spring. I'll be teaching that. This is one that I think, let's see, big data versus data mining. Students, if you had to take only one, students tend to prefer the big data course, find it more fun because it's a lot more practical, using a lot of really cool tools. The data mining course is, let's see, I mean, it has math code because it really is a math course. And if you're a math person, then you'll like it. If you're not a math person, then I hope you still like it, but you'll have to do a lot of math. And then the other third course to do is the graph algorithms course. This is again taught by Professor Sarah Cannon. And this is the course where you're, let's see, maybe like 20% of your software engineering interview questions, those traditional questions, come from the data structures course, specifically related to binary search, trees, and binary search and sorting. But most of them come from the graph algorithms course. And yeah, this is also really much more math heavy than most students expect. I think most students going into a computer science program or a data science program think of computer science as being programming, but computer scientists don't think of ourselves as, we don't think of ourselves as programmers. That we really think of ourselves as mathematicians. All of the upper division courses, pretty much from this point out, are going to just assume that you're good at programming and will give you programming problems and just kind of expect that you're able to figure it out. That what we're going to be really focusing on in the courses themselves and the lectures and the homeworks is what's the math behind the programming, what is it that's actually making your code correct. Talked a lot about in this course about there are different algorithms, and I said you could prove that it's correct if you did these things, but we're not doing that. And this graph algorithms course is the one that's going to introduce you to how do you even go about proving that things are correct or not.
Hey, Mike.
Yeah.
Do you happen to know if graph algorithms is offered next year? I didn't see it in the fall, so I wasn't sure if in the spring it would be.
Yeah, I think it's so for graph algorithms, we don't have a particular schedule about, let's see, so yeah, like big data is normally a spring class. Data mining is normally a fall class. Graph algorithms, it's not like a normally one semester or another. Instead, it's when there's a lot of students who are demanding it. So if this is a class that you think you might want to take next year, say next spring, letting Professor Sarah Cannon know that would be good, so that she can get it offered. But it's, yeah, this is a little bit more of an ad hoc class offered just when there's demand for it.
Okay, that makes sense. Thank you.
Yeah, good question. Let's see. Last thing is that if there's ever anything that I can do for you, please don't hesitate to reach out and ask, whether you're still a student or you've graduated. I've enjoyed having you all in this class and would love to hear from you all in the future, help you out in whatever ways I can. And yeah, so please reach out. So specific things, like if you want advice on classes to take, or if there's some project that you're working on, you want advice on how to do that, or want to get involved in research, those are great things to reach out on. There's probably lots of other things that you might reach out for too, and I'd be happy to help with. Let's see. So next we'll talk a little bit more about the final, but before we do that, any other questions or thoughts on big picture ideas from the course? There's a question in the chat about good open source courses on like edX or those sorts of things. There's, let's see, in terms of particular Python techniques and coding skills, there's a really good channel on YouTube that I like by a guy named Corey Schaefer. It's a little bit hard to spell his name. I don't know if I could spell it in the chat right away, but if you just typed Corey Python, then it's super popular. And he'll go into like detailed techniques about how to use specific library functions in Python. And so it's a really good way to get more coding specific experience and practice about techniques that like no computer science program talks about, because again, the computer science programs and classes at this point going forward are going to focus more on the mathematics rather than the practical aspects of how to do things. Yeah, other than that, I don't have any particular recommendations other than all the things that have generally good reputations are going to be good experience. If you were going to look for like another follow-on course and you couldn't take this graph algorithms course for some reason, taking an algorithms course online through edX or something would be the thing that I would recommend as the best way to improve as a programmer. Good question. Any other questions?
Like, just a quick question. I know that when it comes to advice about tech, whether it be software engineering or product management, one of the things that are always recommended are personal projects and kind of applying your learning. Mm-hmm. So in terms of those personal projects and the application of it, is there any advice you have in how to go about picking projects and how to kind of progress in doing those things and applying the skills we've learned in the class?
Yeah, that's a great question. So maybe I'll first talk about why are those sorts of projects good to have. One of the things that I think students sometimes think is that if you have a lot of good projects out on GitHub, then companies are just going to randomly stumble on your GitHub account and see that and want to hire you because of that. It's true that does happen, but that's like the exception and not something that you should count on. The GitHub projects are not going to be the thing that helps you get the interview at the company. Instead, what a GitHub project is going to help you with is once you have that interview, it's going to be something for you to talk about during the interview and go from getting the interview to actually getting the job offer. And when you're in that interview, what the companies, what they want to see is a couple of things. One, that you have, I guess the language that they'll use often is that you have some sort of passion for programming. And so that means that like when you're at the company, you'll be passionate about whatever they're working on and will go out of your way to learn whatever technologies or techniques you need to accomplish whatever the business task is for the company. I think one of the, no matter what company you go to and no matter what degree you have from whatever school, it's guaranteed that the company is working on a problem that you're not prepared to solve, that you haven't seen the techniques, the algorithms, the programming language. Something about the problem is guaranteed to be new. And that's just the nature of computer science and programming, is that there's so many problems, so many ways to do things that you always are going to have new things. And so the companies, or in the interview, what the companies want to see is that you've encountered that before, encountered a situation where you didn't really have any guidance about how to solve this problem that you've encountered, but you still went out and were able to solve it anyways, because that's what you'll have to do at the company. So the best way to go about demonstrating that is when you have, I guess one of the phrases that people use a lot is that you're scratching your own itch, whatever that itch happens to be for you. So before I came here to Claremont, I was teaching at UC Riverside, and I had a student who was really into collecting shoes. And I don't know anything about shoe collecting other than he would sort of manually go onto Twitter and watch when Nike and Adidas were announcing new shoes, and then be like refreshing the page over and over and over again and clicking the button to purchase it as soon as it came out. And that was a great, and what he did, or what we worked on together, was he developed a system to automate that whole process for him. And so this is a process, this automation, it was just a simple Python script that clicked this button for him automatically and purchased things. And this is a sort of project that, I mean, maybe there's, I don't know how big the shoe collector market is, but the intersection of that with people who are capable of running a Python script is probably relatively small. And it's certainly not something that a company is going to like develop a product and try to sell for. So this student really developed it just for themselves. But it's also like, he got really excited about it, really into it, learned a lot of new technologies. And then when he was doing his interviews, had something really cool to talk about. And most people probably thought that application was like not something that they were interested in personally, but it was something that they were excited when they saw him being excited about it and talking about the different things that he did, and so he got good job offers because of that project. So in that sense, you don't really need to think about like, is there some perfect set of or perfect kind of project that I should work on that other companies are going to like. Instead, you should be thinking about like, what is just something that in my life that I could automate and it would make my life easier. And if you do that, then you're naturally going to be in a position to do the things that companies will want. If you happen to be in the situation where you don't think, like, I don't know, you try to think of as many things as you can and you can't think of anything good or anything that you want to work on, then that would be the sort of time when you can talk to me about doing research with me. And I have lots of projects that that I can give you to work on. The potential disadvantage of research projects like that is that you'll be, I think my projects are cool, but you might not think they're as cool as the projects you're working on for yourself. And so won't get that full, like, same motivation boost. The projects that I'm working on are also really especially geared towards students more interested in graduate school than industry jobs. They still help for industry jobs, but they're particularly suited for students who want to go into grad school. But yeah, I guess that's my advice on that. Maybe one other piece of advice. So one of the things that I've had a lot of success with students is like, okay, you've done a project and now you want to somehow share it with the world and get a lot of users of your project. I've done that, or I've helped students share their projects with the world quite a bit, and I think I'm been reasonably successful at that, helping students with that. So I've linked to a couple of those projects throughout the semester, like the Git game. That one in particular is probably the most successful student project I've helped out with. So that game now has had more than 1 million downloads and has a couple thousand stars on GitHub. So that's a really nice thing for those students to have on their resume when they're applying for jobs. Things that tend to be really successful on social media are things that somehow really capture a programmer's imagination somehow. So things involving Vim and Git and Python, other tools to make you more productive as a programmer, those do really well and get really popular. And those are also the sort of tools that if a company is going to reach out for you because they saw something cool that you did, it's going to be because you did something like that, developing a library for programmers rather than for end users. Good question. Any other questions? Okay, let's go on to our final review. And yeah, so we've talked about the final a little bit so far. I'll just reiterate the format here real quick. It'll be worth about 40 points. And again, we have a little bit more now than 200 points in the class. So it's going to be worth a little bit less than 20% of your grade. That's enough to bump you up a grade or down a grade if you do particularly well or particularly poorly, but not enough to totally make a disaster of your grade. So hopefully not too stressful. Again, I'll post it on this coming Monday, and you'll have all of finals week until Sunday evening to work on it. You can, no time limit, at your leisure. The only requirement will just be that you're not working with other students, and it'll follow the same format as the practice exam. So I'm going to switch my screen now over here to the practice exam. Scroll up to the top. And just highlight some of the things that I think so students in the past have not done as well on as I hoped, and that to focus your study on. So I mentioned this before, but the big O notation, theta, omega, is sort of going to be key to the final and key to your future courses, computer science courses. And so in some sense, all of the questions are going to relate back to these three concepts. One of the things to make sure that you understand is the actual definitions of O, omega, and theta. That throughout the course, we've talked about some of the intuitions behind them and developed some rules of thumb that you can apply about when something is one versus the other. But anytime you have any doubt about it, you can always go back to this definition and get the correct answer. And so this definition right here is from the notes from week 2 in the class. So you can go back and refer to the definition here. There's also a formal definition on Wikipedia that is, you could look at that one as well. I think this definition is slightly easier to use. So this is the one that I recommend using. This is the one that, I won't say I have it memorized, but I can recreate it from scratch. And you should be able to recreate this definition from scratch without thinking about it. Thinking about, okay, I know that something that's n is O of n squared, And so what do I have to make the definition be like in order to make that happen? But yeah, you should be able to, I'm not going to ask you to reproduce these definitions exactly. If this was a timed in-class exam, I would ask you that because these are like just foundational things that you really need to know these definitions. And those definitions directly answer all of this first question, this first problem here, that you just do this division and take the limit and you get the answer. This is not a calculus course, so I'm not testing you on, do you know how to take the limit of a particularly complex function? You can always, if you don't know how to take the limit, just plug it into Wolfram Alpha or any other limit taking system, and it'll compute the limit for you fine, and that's it. That's all you have to do. Very common things that you should pay attention to are the problems that involve logarithms. Every year students make lots and lots of mistakes on problems involving logarithms. That's the most common source of mistakes. So in particular, the bases of the logarithms don't matter for asymptotic notation. Bases don't matter. The logs are always less than polynomials. Polynomials always less than exponentials. Doesn't matter what the numbers are. They're always less than. Polynomials inside of the log, based on the rules of logarithms, that 3 can come out, and so it's just a constant factor. So these two things are exactly the same. This one here is a relatively complicated one. It's related to the proof. It's inside the book. We didn't really talk about it in detail, though. I just mentioned it in class. But the proof that any search algorithm, any sorting algorithm that relies on comparisons, so greater thans or less thans, the fastest possible sorting algorithm is in log n. The proof of that's in the book. So the proof of these two things are actually equal to each other, theta related to each other. The proof of that's in the book. You can also still just use the definitions that we had, plug the formulas into Wolfram Alpha, and it'll come out as being theta. And then these exponentials down here, because these exponentials exponentiating are outside of the logarithm, it's different than this right here. And so these are not equal, whereas these ones here are equal. And so it's very important to pay attention to that on the final exam. Any questions about, so you will on the final exam have a problem that looks just like this, just with different formulas in here, and you'll have to be able to answer all of those. Any questions about what that will look like or how to do that?
So if we use Wolfram Alpha and the result is like, so the limit when n is closer to infinity and fx over gx is equal to infinity, and how do we like match that with the definition?
So if we come over to the definition here, then if you got f over g equals infinity, then you're not in this case right here, because this is only less than infinity. Equals infinity is greater than 0. So you are in this case, and not in this case, because theta has to be both. So in that case, if f over g equals infinity, it's omega. I'm not sure if that's answer your question.
Yeah.
Or okay.
Yeah, that makes sense. Thank you.
Mm-hmm. And again, you don't have to show your work at all for this problem. Actually, really for any other problems, it's just going to be you either got it or you didn't get it. I think the true false is going to be another spot where a lot of students miss points. And again, here, any answer that is incorrect, it's not a 0 on it, it's a -1. So you want to make sure that you are paying very close attention to all of these statements in here. And there's going to be a lot of statements that really test, say, your understanding of asymptotic notation, like this first one here. And so be really, really careful with those statements. My, I guess, personal recommendation on how to do this is go through it once, answering all the questions, and then put it down, come back another day and go through it again, just so that you have a fresh mind and can see maybe some subtleties of the question that you didn't see the first time. I'm not going to be asking what I consider to be trick questions, but you might consider these things to be trick questions because they are going to be like very subtle, really require an understanding of the fundamentals. Let's see, so problem 3 here with the difference between lists and decks. That's another important distinction to pay attention to. We have that wiki page from the Python documentation that has all the runtimes for all the data structures. The questions that I ask on the final could involve lists and decks, sets and dictionaries, anything from that wiki page, and you'll have to be able to plug them in here and figure out the runtimes. One of the common questions that people have asked so far is that with these generator functions, so like range and enumerate, what is the runtime complexity and the memory usage complexity of these functions? And all of the built-in generator functions, so range, enumerate, and then we also talked about map and filter in this class. All of these built-in generator functions have runtime and memory usage of O(1) constant time. And that's the advantage of these functions over non-generator equivalents, because we're using that generator, that yield keyword, and that iter and next magic methods. It's more complicated to implement, but you get that constant time runtime in memory. And this is widely used throughout all Python code. And yeah, so very fundamental concept that you're guaranteed to run into over and over again in Python. Let's see. My guess is that, or historically, students have done reasonably well on these sorts of questions because you kind of understand that there's some difficulty in here and spend the proper amount of time on it. And these sorts of questions and these sorts of questions are where students tend to be overconfident and not spend enough time on it. Here's the recurrence relations. I'm just going to work through this problem as a review right now. It's been a long time since we've done this, and there's a lot of important things going on inside of here. So this question is problem 4. It's asking in 2 parts. What is the runtime of this trinary search function? And it's divided up into 2 parts. The first part asking what is the recurrence relation. So again, the recurrence relation is when you have something that looks like T of n equals a T of n over b plus f of n, something along these lines. Anytime you see this word recurrence relation, this is the format of what your answer should be in. And then we'll use the master theorem to solve this for an actual asymptotic notation. And anytime you have a recursive function, the way that you analyze this recursive function is through these recurrence relations. In practice, there's maybe, I don't know, 5 or 6 different recurrence relations that come up, and programmers just have those sort of in some sense built into our blood, that you've done it enough at some point in your career that there's no need to write this out explicitly and go to the master theorem for those standard situations. And yeah, 99% of situations are those standard situations. It's only when you get into like the research level academic computer science that you get out of those standard situations. So how do we write our recurrence relation as something like this? Well, every line in our program, again, will write what is the runtime of just that one line. And so here, nothing going on, so put a 1 for constant time. Here we have a function call to the length function, and the length function can take a different amount of time depending on what our data structure is. So again, you always have to be clear, what is the data structure that we're calling this on? In Python, again, Python is an untyped language, so there's no guarantee that I'm writing trinary search thinking that it's going to be a list passed in. There's no guarantee that it's going to be a list passed in. Any type of container could be passed in. And in particular, in this case, a deck could be passed in, and we get something very, very inefficient if a deck was passed in. But in this case, it's a list being passed in, and so we'll use all of our list runtimes. And we know that the length of a list can be calculated in O of 1 time. Anytime you're defining a function, so all of this is just the definition of the function, defining it still takes constant time, O of 1 time, no matter how complicated the function is. It's only running the function that takes non-constant time. And down here is where we actually run this function. So here, when we have our recursive call right here, the recursive calls are where you put that t value, and we have, in this case, t of n. Actually, in every case, it'll be t and n, t of n when you first call it. The thing that we have to do, though, is pay attention to what exactly is in. In our case, n is going to be the total size of the list, the total size of the container that we're doing our recursion on. And that would mean that n equals right minus left. And so because right is the length, left is 0, so it's just, we're calling it on something that's the size of our container, which is t of n right here. Now when we're going, because we're calling this go function, now we actually go inside of the function, and now we're calling it, not defining it, so we have to look at the implementation details. Our if statement right here is not calling any functions, it's just doing arithmetic, so that's constant time. Let's do this in green. Here, 1. The return statement is, has a number of things that we have to think about. There is this slicing operation right here, and for a list, slicing is O of k, where k is the size of the slice. Here we have left and right as our slice. So the size of the slice, again, would be right minus left. And so you might think that size of the slice would be n, just like right minus left was n over here. But now we've, inside of this if statement, we have this guarantee that right minus left is less than 3. So it turns out to be just be a constant. So because of this if statement, this here is a constant. And what this if statement again does is it's our base case. We have this return. The return has no recursive call, so this is our base case. And in general, the base case is pretty much always going to take constant time. Not guaranteed, but for most applications. Then we also have this in right here. And the in operator, again, does that underscore contains function. And for a list, that takes time O of n, where n is the size of the container. The container here is not the full excess, but the sliced excess of left colon right. So the size of this container, because we're in the base case in this if statement, is still only n equals 3 and not our original n. So it's still only O of 1. And so this whole line right here takes time O of 1. And there was a lot of things that we had to think about in order to get that. Had to see that there was a function call here, had to see that there was a function call here, think about both of those runtimes, and in this case, they happen to both be O of 1. If you're in the base case, they'll probably both be O of 1, but you still have to be careful about that. When we get to non-base case things, they're not going to be necessarily constant time. Then we have the mid 1 and mid 2 lines right here. Again, it's just arithmetic, no container operations. So those are both going to be constant time. Just write 1s instead of O of 1s. Here we have our hidden function call right here of doing an index. And in a list, because we're in a list, this is O of 1. But if we were in a deck, this would be O of n, where n is not the size of the slice or the size of the smaller container, but the actual full size of excess. So this is the line right here that would be super inefficient if we were doing it on a deck. But because it's not a deck, because it's a list, it is efficient and we get constant time like this. Now we have 3 recursive calls, this one, and this one. And the recursive calls are where we're going to write out our T formula. In each of these cases, so we have to put something inside the parentheses over here, representing the size of the new problem that we're recursively calling on. And what goes inside of here is whatever the size of the problem is defined by these parameters. Here we have mid 1 minus left would be the size of the problem. And based on my definition of mid 1 up here, I know because we're dividing by 3, so right minus left is our value of n, the size of our container at the current iteration, right minus left, n equals right minus left down here. Because I'm dividing that by 3, I know that the size of this problem is going to be n over 3. And that's the same holds true for these other recursive calls as well. N over 3 and n over 3. The if statement, there's only one last line to check. This if statement right here has the same runtime as this if statement right here. Just less than is constant time, indexing into a list is constant time, so that's constant time as well. And then the else statements are always constant time. So now when we're adding all of this together, our final runtime is always going to be the T of n, and then we add all of the things inside of our recursive call together, collapsing things using the sort of implicit big O notation. So there are 3 calls to T of n over 3 right here, but we're guaranteed to only call one of those on each iteration. So even though there's 3 calls to n over 3, it's still just T of n over 3 right here like this. And then there's a whole bunch of constants, 1s, add those together. I could write, if I wanted, something like plus 10 over here. Sort of doesn't really matter what the constant factor is though. And so it's more traditional for people just to write plus 1. And again, that's sort of like implicitly plus O of 1, but again, just tradition to leave out the big O asymptotics when writing a recurrence relation like this. Yeah, so lot of small things being tested on a problem like this that you're able to do. So I want to make sure that we get to have time to do the master theorem. So if you do have questions on this, hold them. I'll take them in a little bit, and I'm just gonna go ahead to the master theorem part on the second part down here. And yeah, so on your final exam, you are going to have to create at least one recurrence relation, and then you are going to have to solve at least one recurrence relation using the master theorem. The reference for the master theorem that you should be using is the Wikipedia webpage. Again, I like to have free resources, and so that's what we'll use. Wikipedia is actually, I don't know, it's better than the vast majority of textbooks on computer science issues, at least as a reference perspective. And if you're looking for more problems to work on related to the master theorem, week 5 is the week in class that we did this, and the lab has a lot of good problems that cover all the different possible cases. So if you can do all of these, then you'll do well on the final. Okay, so the hard part of the master theorem is just reading this big giant table right here. But before we get to reading the table, we have to calculate this secret value, log base b of a. And so coming back over here, our b value, again, this is the a out here, this is the b right there, that 3. And so we have the log base 3 of 1. And this is a, let's see, if you're not confident in your logarithms, then you should just plug this into a calculator and get a numerical approximation for you, because it'll be easier to work with this with some sort of decimal representation. In this case, when you take the log base anything of 1, it's always going to be 0. So our secret value, secret is going to be 0 for this problem. And now we have to consider each one of these 3 cases. My recommendation is to, or at least the way I approach these problems, is I always start with case 2, because most problems come into this case 2 category. Probably like 60% of problems are case 2, 30% of problems are case 3, and 10% of problems are case 1. So because of that, I start with the case 2. And what we need to check is in this column right here, comparing our f in value to this expression over here. And I think this is the thing that how to do that is something that is really confusing for a lot of students who, especially maybe not math majors, not taken a lot of math courses yet. And the reason for it is because there's no one particular k value that you have to check. In some sense, you have to check all possible k values, every k value from 0, 1, 2, 3, 4, 5, 6, 7, 8, all the way up to like infinity minus 1, if that were a real number. And if it works for any one of those k values, then you're in this situation right here. In practice, k is going to be very small, typically 0, 1, or 2. And I can't say I've ever even seen a problem that k is bigger than that, but it could happen. But so at least make sure that you check explicitly for k 0, 1, and 2 if you don't feel comfortable like doing every possible k and reasoning along those lines. Here, so now we have to check f of n equals this complicated expression. I'll write it down here. F of n equals, so incrit log k n, whoops, there we go. F of n equals n to the c crit log to the k of n. Did I get that right? Log to the k of n, yes. And so secret here is 0. So this whole expression, this whole factor right here goes to 1. And we only have this factor over here to consider. Let's scroll up, find out what is our f of n in this expression over here. Our f of n was 1. So we need to set this whole thing equals to 1. And now our question is, can we solve this for k? If the answer is yes, then we're in this situation. If the answer is no, then we are not in this case. And it turns out that we can solve this for k, in particular by setting k equals to 0. If we set k equals to 0, then this whole thing becomes 1. 1 times 1 equals 1. And so because there is a k that I can solve this equation for and actually solve it, that's why we're in the second case of the theorem. So it means we're in the second case of the theorem. And so our master theorem bound is this expression right here, very, very similar to our previous expression. It's really easy to get these two expressions confused when you're working because they're so similar to each other. But the only difference between the check expression on the left-hand side and the value expression on the right-hand side is that we have a +1 on our k on the right-hand side. So if I come down here, write out that actual result, and this is the third column in the theorem, we get T of n equals theta of n secret log k plus 1 of n. Secret was equal to 0, so again, this whole factor goes to 1. K, the k solution was 0, so this is log to the 1 of n equals theta of log n. And this is our runtime of trinary search. One of the sort of principles that we mentioned before when comparing binary search versus trinary search is that they both have the same runtime. And it turns out it doesn't matter how many sort of splits you choose to do, whether it's 2 or 3 or 4 or 1,000, you're still going to get the same same final runtime down here, and as logarithmic runtime. And so because of that, everybody always uses binary search because it's the easiest to code and gives you the same good runtime. The way to know that if you're in one of these other two cases is you're not in this case, so you must be in one of the other two cases. And now when you do your check, if you're, again, when you see the omega, that's like a greater than or equals. This is a lower bound. And so if your f function is bigger than this over here, then you're in this case. O is an upper bound. It's like less than or equals. So if your function is less than or equal to this over here, then you're in this case. But again, it's like 60% case 2, 30% case 3, 10% case 1. That's pretty much it for our review. I have office hours now, so I'll stick around to answer any questions that anybody has on these problems. But that is the end of our official class today. I would like to ask you all to please complete the course eval if you haven't done that yet. That's really helpful both for me in planning future courses on data structures and for CMC in order to know how to structure our course offerings more broadly. So please do that. Yeah, I've really enjoyed having you all in this course, and thanks for sticking with us through the online format, and I hope that I will get to meet all of you in person this coming fall, those of you who are going to be coming back, and those of you who are graduating, I hope I get to meet you at the commencement ceremonies that are going to be happening. Yeah. Again, I'll stick around to answer any questions that you may have. There's probably a number of questions about the problems that we're just working on, but otherwise I will, and tomorrow we still have the lab time. I'll be available during the lab time to answer more questions about class, the final, anything, or to answer questions on your graph programming assignment. But otherwise, I will, yeah, have good luck on all of your final exams and final projects and things like that.